All right, welcome. Today, we are going to crack the secret language that powers everything from your favorite video games to the photo editor on your phone. We're talking about geometry in motion. Have you ever really thought about that? You know, when you tap a button to rotate a photo, or you watch a character in a game just flawlessly leap from one platform to another? What is actually going on under the hood? It feels like some kind of digital magic, right? Well, surprise, it's not magic at all. It's a precise, really powerful, and actually pretty simple language called geometric transformations. And by the end of this, you're going to know how to speak it. Okay, so just like any language, you got to start with the alphabet, right? Well, for the language of motion, our alphabet only has 4 basic letters, or moves. Let's get to know them. All right, first up, we've got translation. This is the simplest one. It's just a slide. Picture pushing a chess piece across the board. It's not turning, it's not flipping, it's just sliding from one spot to another. That's a translation. Next up, reflection. This is the flip, and this one's easy. Just think about looking in a mirror. Your reflection is a perfect flipped version of you, right? In geometry, we do the same thing, just flipping a shape across the line to get that mirror image. Then there's rotation. Super intuitive, right? It's the turn move. Picture the hands of a clock spinning around that center point. The whole shape just pivots around a single fixed point. Simple as that. And last but not least, we have dilation. You literally do this 100 times a day on your phone. It's the resize move. When you pinch to zoom in or zoom out on a picture, you are dilating it. You're making it bigger or smaller from a center point. Okay, so we've got the basic moves down, but for a computer to get it, we need to turn these ideas into really precise rules. This is where we go from just feeling it to actually coding it. We're turning pictures into algebra. So, how do we write this secret code? We use something called mapping notation. It's really just a simple instruction that says, hey, take any original point, x, y, and follow this rule to map it to a new point. We call that new point x prime, y prime, which is just a fancy way of saying the new x and the new y. This is the basic grammar of our code. Let's start with the code for translation. To turn that slide into code, the rule is so simple, you just add. If you want to slide a point, you just add a to your x and b to your y. A is your side-to-side move, and b is your up and down move. Simple. So point P at 2, -1 moved by 3, 4. Well, 2 plus 3 is 5. And -1 plus 4 is 3. The new point is P prime 5, 3. Reflections have some super simple rules too. And these are definitely worth tucking away in your brain. Look at this table. If you want to flip something across the x-axis, all you do is flip the sign on its y-coordinate. That's it. To flip it over the y-axis, you flip the sign on the x-coordinate. Each type of reflection has its own predictable little recipe. Rotation's got its own little recipe too. Now, for the most common one, a 90-degree counterclockwise turn, the code is x, y turns into -y, x. So check this out. It's a 2-step dance. First, you swap the original x and y. Then, you make that new x value negative. That's it. So our point B at 4, 1 swaps to 1, 4, and then we just negate that new x value, landing us at B prime -1, 4. And our zoom move, dilation? Oh, this is the easiest one of all. You just multiply. If you want to make a shape twice as big, that is, a scale factor of 2, you just multiply both the x and y coordinates by 2. So our point C at 2, -3 gets a whole lot bigger and becomes C prime at 4, -6. All right, alphabet learned, time to write some sentences. Because when you start combining these simple moves one after another, you can create incredibly complex actions. It's just like writing a computer script. So here's the absolute key to the whole thing. You get those really cool, complex movements by doing the simple moves in a sequence. But, and this is a big but, you have to remember that the order matters a lot. Trust me, just like trying to put your shoes on before your pants, the order is everything. Okay, let's actually walk through a script together. We're starting with this triangle ABC. Step 1, we're going to reflect it across the y-axis. And what was that rule again? Right, x, y becomes -x, y. So we just flip the sign of each x-coordinate and bam, we get our new triangle A prime, B prime, C prime. Okay, now for step 2. We take that new triangle and we translate it by 2, 0. The rule for that is to just add 2 to every single x-coordinate, and that gives us our final shape. See? 2 simple moves created one totally new result. Okay, you ready for a pro-level tip? something that'll really change how you see these problems. To really master this stuff, you don't just look at what's changing, you gotta look at what doesn't change. And that brings us to this really powerful idea called invariants. Invariants are just the things about a shape that stay the same, even when everything else is moving around. So as that triangle we just moved was flipping and sliding, what wasn't changing? Well, its side length stayed the same, its angles didn't change. Focusing on those preserved properties is the secret to solving the really tough problems. And here it is, the invariant cheat sheet. Just look. Translation, reflection, and rotation, they all preserve length, angles, and the overall shape. They're called isometries because they don't change the size. But, and this is the big one, look at dilation. It keeps the angles and the shape the same, but it does not preserve length. It changes the size. Knowing that difference is a huge advantage. So who cares, right? Why does this even matter? Well, because this is how you solve the hardest problems. If you can prove that one really complex shape can be turned into another one through a series of these moves, you've proven they're fundamentally related. It's like finding their shared DNA by focusing on what stayed the same. Okay, you've learned to write the code. Now for the real test. Can you read it? Can you reverse engineer it? Take a good look at this rule right here. What combination of slides, flips, turns, and resizes could possibly turn a simple point xy into this? I'll leave you with that. That's how you truly master the secret code of shapes.